Imagine someone hands you 100 rupees and tells you to buy as many chocolates as possible. To walk away with the highest number of items, you don't need a complex map. You just look for the chocolate with the smallest price tag and grab it first. Then you look at your remaining money and do it again, picking the cheapest option available at that exact moment. You repeat this until your money is gone. This strategy of choosing the immediate best option to reach a specific goal is exactly how a greedy algorithm thinks. Formally, a greedy algorithm is an approach that selects the best available choice at every single step, without considering what happens later. It focuses entirely on the present. Our intuition often defaults to this because it's simple. We stack up these local, immediate wins, hoping they will eventually add up to the best possible final result. In algorithms, this is the local optimum, the absolute best choice right now, looking only at your current step. But the true goal is the highest peak, the global optimum, the ultimate best final answer for the overall problem. We use this logic for optimization problems. It's what you use when you want to pack the most value into a knapsack, or when Google Maps looks for the shortest possible turn at a junction. The process follows a strict flow. Find your choices, pick the best one, and never change it. You lock it in and repeat. This is an irrevocable decision. It cannot backtrack. Once past a junction, the path is sealed, even if it was a mistake. By removing the ability to go back and check other options, the algorithm becomes exceptionally fast. However, it also becomes rigid, making it blind to better paths that might have started with a worse first step. Let's see this in action. Make 16 rupees using the fewest coins, 10, 8, and 1. Greedy grabs the 10 plus 6 ones, 7 coins total, but the best answer takes just 2 8s. Greedy failed because the immediate choice led to a dead end. To avoid this, problems need 2 criteria. First, the greedy choice property. A local best choice must align with the overall best solution. Second, optimal substructure. After making your first choice, the remaining problem is just a smaller version, solvable using the exact same logic. If a problem doesn't have both of these mathematical traits, a greedy approach is guaranteed to eventually give you the wrong answer. The trade-off is clear. You get high speed and low memory usage because you aren't calculating every possible future. But you sacrifice accuracy unless the problem fits those 2 specific rules. For your exams, remember, a greedy algorithm is a strategy that makes the best possible choice at every stage to find an optimal solution without ever reconsidering a previous decision. In the next modules, we'll see how this works in the real world through Huffman coding, the fractional knapsack problem, and Dijkstra's algorithm. Success with this method isn't about the code. It's about looking at the coin denominations or the map junctions and proving those 2 rules apply before you take the shortcut.